a lot. Good afternoon, everybody, and sorry that I can't make it in person today, but I will be there on Thursday. So you can ask me all the questions you want on Thursday in person. I don't want to indulge into the HR and industrial engagement entirely, but want to focus on the activities we do at the HIT Institute. And we quote this, the transformation to digital coating chemistry, indicating that we make use of automation and digitalization in order to... Hello? Yeah. Okay. So that I have an issue here. I'm getting confused. Okay. Can't talk like this. I get an echo from my voice. I don't know if you can do anything about it, but you can hear me, but I hear me twice. And that is difficult to talk. Anyways, I try to talk slowly so that I'm not confusing myself. So, transformation to digital coating chemistry, what does it mean? Can you still hear me? Okay, I'm assuming you can. ELOC Institute is in operation for more than 15 years, conducting research at our university in the area of coatings and paints. And since 2017, we have added the HIT Institute and preparing ourselves to the transformation towards coating chemistry. What is changing is indicated by the two pictures. On the left side, you see a young lady in the lab doing manually what experts like to do, mixing colors or coatings. And on the right side, you see Lasse, who's in the auditorium, preparing a workflow and telling a machine, a robotic system, to execute this preset workflow. So besides the chemical expertise that's manifested in the workflow, in the modules, we also have a lot of automation and robotics functionalities. If you take a look at our floor plan, you see to the left the outside of our building, you see the control center for the system, and you see a floor plan of our system. You'll see that we copy the three major steps of a formulation expert, and that is preparing a formulation, applying a formulation, conducting some tests in the process between formulation is ready and application has started, for example, pH investigation. And then in the end, we have a coated substrate that can be characterized. If you take an even closer look, you see a lot of functional units being able to do the storage, the liquid dosing, the powder dosing, dispensing, filtration, drawdown, etc., etc. Just keep in mind what sounds so simple for a human being once trained in the lab is certainly a challenge for the automation and the robotic system. However, the benefit to have a system like that is that we can run, depending on the workflow, something between 40 and 120 samples a day. And that without compromise in performance. And, you know, that is a huge number compared to typically 10 to 20 samples done by an experimentalist in the laboratory. Now, this is what the University of Applied Sciences is doing. This is what industry is doing. So this is, you see the YouTube link up there. This is from Irene Gorman from BASF. And they have set up what they call the Digital Material Profiling Lab. So the idea is that of every formulation they prepare, they take a sample and qualify that sample. So put the information, what has been mixed, along with the quality of the prepared surface into a database. They can run up to 200 samples a day, including the formulation, application, curing, and storage. And from the storage, they can take the substrates and conduct profiling tests. That can be a simple inspection, like with a scanning microscope. So you see that false image to the left, bottom left, showing that this surface is by far not perfect. They also use standard systems used in industry to qualify appearance, gloss, things like that, color. And they also have included a nano scratch test to investigate mechanical properties as well as chemical properties of the surface. In the end, the main challenge is to put all this data into a data management system. So because we have a robotic system, we automatically have an electronic lab notebook. Every step that's been taken with the sample is documented and gives precise information of what has been done. The information is readily available in the central data management system or in a database called repository, where everybody at BASF has immediate access, of course, everybody qualified. So they have a streamlined data sharing worldwide. So everybody can now use his or her tablet to inform himself or herself about the performance, broaden the knowledge base, and that's of utmost importance for the industry or industrial users. They have a fast and, because of the automation involved in the preparation and testing of the sample, superior solution. And for this, they get applaud from their customers because they have now readily available solutions. We are not industry. We cannot afford making many samples. So we thought of a slightly different approach, connecting the input parameters. For example, for a typical paint or coating, it consists of binders, pigments, fillers, additives, and solvents. So we take these raw materials as input parameters and try to correlate them to the application properties. That might be color, that might be scratch resistance, adhesion, and so on. So for us, it is a mathematical problem. We take the raw materials as input variables, and we try to build a functional correlation between the input variables and the attributes. And this is done concurrently. So when we do a typical formulation, it can have up to 20 input parameters. And simultaneously, we want to optimize 4, 5, or even 6, 7, up to 10 properties. And so that is quite a daunting task. And if you would do that in a true design of experiment, you would do thousands of samples. Our idea is to use an advanced machine learning algorithm comprised of a Gaussian process and a neural network. And this algorithm learns the relationship, the functional relationship between the attributes and the variables. We call this the I-hit solution engine, and I'll show you what happens with the mass that is needed to execute this circular approach, this iterative approach. The slide here is taken from Kevin Kremans. He was part of our DNL HIT project, and he developed together with Christian Schmitz this concept. So if you look at to the left, you see the cycle, this I-hit solution engine cycle. We get a task, so somebody defines the input parameters, and then the algorithm takes over, designs the number of samples in a first iteration. Execution is done automatically in the lab as well as the testing. And then based on the test results, we start building a model. So in the first iteration, you see to the left, you see just 2 points. And these 2 points indicate not well understood what's going on. Unfortunately, I have to realize that the animation is not working, so apologies. There should be an iteration going on up to 10, and so we have 10 discrete points resembling quite nicely this curve. But let me show you a practical example conducted together with a small company nearby in Venlo, Drost. And what was the task of this approach? They wanted to take an existing product and change it to bio-based. Changing something to bio-based means that at least 60% of the raw materials are made from renewable resources. So the task sounds simple, right? Just look through the list of ingredients and identify those you want to replace and find that new formulation with slightly different ingredients. Of course, if you look to it more detailed, you see a number of parameters, the input factors that can be changed, and the number of outcomes or outputs that should be kept constant, because we still want to have the same performance of this now bio-based material. If you would do that in a classical design of experiment, you would end up somewhere between 250 and 6,000 experiments. Now, what we have done is we gave that problem to our algorithm, and the algorithm suggested in total 4 iterations, 50 experiments to converge to a product that is more or less from its quality, from its output performance, comparable to the previous product. In this particular case, we exchanged the resin as the material that was simplest to be exchanged to bio-compatible raw materials. So the 0 stands for the original fossil-based resin, and 1, 2, 3 is the bio-based one. And you see that in total of 4 iterations, so 3 adaptations, where the algorithm learned how to replace and what to do in terms of percentage and so on to this material. And in the end, it found it proposed a formulation based on resin number 3 that is comparable and partly outperforming the original product. You see in the top right chart the number of experiments and one of the output parameters indicating that indeed we get hardly any yellowing. So the resin is really showing a nice performance over time in bright sunlight. The model has been evolved in that plot you see to the bottom. So the black dots indicate actual measured data that are used to build the model. The bright area is in the middle is indicating the best fit to that model, while the areas above and below indicate an uncertainty where we can see that the model in this entire area is more or less certain to a degree of plus minus 5%. And you can make these kind of plots for all output parameters. So this, for example, is the output parameter water resistant, and we have plotted the 2 main indicators for this property. So how do we find these indicators? So the information is, in this particular case, it's another indicator, hiding power. So how well can my coating cover a black and or white chart? And you see the sensitivity analysis of my model indicates that the thickener is the most dominant factor responsible for hiding power. That is a chemical information. However, we also see that we can use process parameters. For example, when we do spray coating, the way we do the spray coating, so how the cone of a sprayed material is overlapped, has a significant impact on the quality, as well as the mixing properties and so on. So the take-home message here is that with the model, I can make a chemical or a process and chemical analysis of the properties responsible for certain output parameters. Of course, this is not the end. Despite the fact that we spend a lot of money on this system, it is never complete. And so we also do automation research here at our institute, especially together with colleagues in our electronics and computer science department, and we look into how can we perform scratch tests or hardness tests on coated substrates, and how can we use image recognition to automatically analyze the information from the coatings. You can also use spectral information, here indicated in another experiment where we had different powders, different color powders, and we mixed them and we tried to understand how the spectrum looks of these mixed colors. So the input for modeling is a measured spectrum. And the output to the right, after we learned or taught the model, you see quite well that the predicted color from a given formulation is really confirmed by the experimental data. So it's not just one color or LAB color code that can be derived from a model, but it can also be an entire spectrum. Of course, we have continuously applied for funding in order to further advance our expertise. And you see one of the recently funded project, FR cooperative project, together with 2 industrial partners, focusing on color application, Hesse Lignal, and on automation solutions, Orontech, where we kind of pursue how we do develop an intelligent infrastructure, we call it, for automation, for automated formulation of coatings for the digital coating industry, and more importantly, how we can, as humans, interact with an automated system like this in the most efficient manner. So I will report in 3 years from now about progress from this project. But it's indicative of that even smaller companies like Hesse are interested to engage in the digital coating chemistry solutions, and that automation companies like Orontech have developed or are still developing expertise in chemistry. What is the future? This is from a presentation from last month's LAC-Tagung, so coating show. An expert meeting in Würzburg, and this is from BASF in Münster, where they kind of predict how the future may look like. So a real coat is typically not a one-layer coating, but it consists of a number of steps and a subsequent layer. So the steps, for example, for a car coating consists of the substrate, a chemical treatment of that substrate, so it can be steel or aluminum. Then there is an electrodeposited coating, an e-coating it's called. Then there is a first primer on top of it, an organic coating, then the base coat responsible, for example, for the color, and then a clear coat. So quite frankly, this is a complicated system. It's just not one chemistry, but it is 4 or 5 layers of chemistry with interface layers in between. André Swart gave a presentation how he predicts the future to be, and I'm not sure if that's going to happen quickly, but it gives you at least an idea of the motivation. So it is about stone or rock impact testing, and the status quo is indicated here. You see the familiar steps, I guess, now for formulation preparation, application, in this case by spray coating, then impact testing. So in this case, you take kind of distributions of rocks, small pieces of dirt, and under defined conditions, throw them onto the surface. And then you have a human being doing a visual inspection. The typical cycle time of this process is 4 hours. So it's a subjective analysis in the end, the human expert. It's a time-consuming 4 hours. And it's, of course, expensive as you have time spent in the lab and so on and so forth. The idea is that you build a physical model of it. So to the left, you see the 2 bottom layers, the e-coating layer and the primer. And you develop or you try to understand how the cathodic dip coating, so the e-coating, shows a defect development upon impact of a projectile. And this is the standard process for making that coating system. And this is an advanced model where we have an adjusted Young's modulus in the top protection coating layer. And you see that upon impact, that we don't break through the E-coat layer, this red dot indicated here, but that we have, because of the elasticity and the damping from that top coating, we don't scratch the surface, so we are still corrosion protected. The amount of time spent on the simulation is 20 minutes, and BASF claims, of course, once we have a model like this, we can cut back on development time of 80% and more. So the motivation is obvious for the coating industry to pursue the digital transformation, as it promises accelerated product development. Now, this is big industry with big money. How is a research institute pursuing that idea of digital coating? You see an image here from the Cronin's group at the University of Glasgow. You see the familiar lab bench space, and you see, maybe not quite obvious here, but you can watch a video here at chemify.org. You see a lot of instrumentation providing digital information. His vision is that a system like this interacts with a computer and the internet, finds paper in a database, and then repeats a chemical synthesis automatically in the way I described. You know, it pursues a certain iteration, learns something, and continues this iteration until it has a good model, a better understanding of what's going on. The Royal Society of Chemists in Great Britain has, in 2020, provided a lot of information about the digital future of chemistry. It's certainly worthwhile looking at it. If you have enough money, and again, you play with big players, the KIT in Karlsruhe, as well as BASF, you can make your own synthesis robot. And this is shown here. So now we are not taking an existing lab bench, but we're looking to something in the order of 3 to 5 million euros, where you, quote unquote, have full automated control of the chemistry going on in order to make new substances, and later on continue doing high throughput chemical reaction monitoring. Another faculty in Canada, Jason Hein, he pretty much says we have a modern discovery pipeline. So if you take your material properties, your fundamentals in chemistry, you understand the reaction mechanism, and you have some sort of automation system, you really can jump into the digital world and provide, based on data, modern and new chemistry. So really what's next for us as a university is not just take what we can get in terms of raw material from the market and make a best formulation / product of it, but to really take a closer look to the chemical functionalities of the molecules from each of our chemicals and try to correlate how a certain functional group is responsible for certain properties of our final formulation. So really what we are interested in is not taking a binder, but taking the binder molecule or the chemistry of the binder and correlate it to the output properties. This is straight jumping into material or digital material, and there's a huge effort going on. You can find more about it in materialdigital.de, where there is a holistic approach, of course, driven yet in this case by academic institutions and not by industry, where you really have a good chemical understanding of the raw materials, the engineered materials, the processing, the scale up, the product properties, and how it behaves over its product life cycle. So, you know, you may have heard about sustainability, and this is really a complete cycle with an optimized sustainable material cycle. So what this implies is you need to have access to the information, to the data along the entire life cycle here, and they have to be fair, that is findable, accessible, interoperable, and reusable. So this is the driving force, and they have quite a number of real-world projects to indicate their support or their progress in this direction. What is, and that's a comment that's necessary here, what is easy to do is to combine the electronic notebook and the databases with research institutions. Researchers are known for sharing their information easily in publications, for example, and so they are willing to work together for what they call the National Research Data Infrastructure for Chemistry. So this is something you can set up easily, and you can even combine it with legal or policy terms that impact the industry quite a lot these days. In these databases, you can find a lot of information. You can find the chemistry, so the molecules, for example, the properties of these molecules, then the reaction and what comes out of it. And you see that there are a number of quote-unquote information or contributors to this database. But it is not an industrial database. It is really from researchers. That brings me somewhat to the end. So I call this summary, but I have a few more slides to share. I hope I could show you that from a traditional basis where you are an expert in chemical formulation for coats and paints, and you have a knowledge of your raw materials, which will change in the future from primary, that is fossil, to secondary, that is renewable or even recycled materials, that with this in mind, or this as a basis, you can use automation solution in a joint fashion. So I would never claim we do it 100% automated. We always have a human contribution in that automation process. However, we don't do it simply high throughput, many samples with a variety of materials or mixtures of materials, but we do it in an intelligent way, developing a digital model that becomes our chemical expert for this particular formulation problem. With this, we hope contribution using Chemistry 4.0, that is automation and digital, to provide sustainable solution for surface technologies. Now, the last picture shows the invitation to a workshop we held here in Krefeld beginning of the year, where we explicitly invited chemistry to give us their opinion on how we go about the digital coating future. And what came out of it is a slide something like this. You know, you see the chemical world here indicated by the raw material, the chemical processing, the manufacturing, and the application. And you see the data world, the information, the data sheet from your raw material, the process parameters, the scaling up and materials in the manufacturing. And this has to come together. I showed you bits and pieces of it, but it's still a long way to really connect chemical material world and digital information. We suggested a DNA molecule that's slightly rotating to kind of mix the two worlds together over time. I showed you work done on the hardware side, on the chemical side from BASF. I also want to show you that you have readily available information technology solutions. This is from a company in the United States, Uncountable. They pretty much pursue the same idea that I suggested initially, you know, that we have the raw materials and insights on our application, but they also have tools for example, do the scale up. So what I do in the lab is not necessarily that's working in production. And so they use all these familiar terms, and they have a commercial product, a software product that supports your research. So in the end, I think that we are ready for, at least in part, tackle some of our grand societal challenges. You've heard about the European Green Deal and sustainability and resource efficiency, et cetera, et cetera. So these are the words that actually give you funding quite a bit. We are reaching out to industry to quote unquote join forces with them. So we started a strong interaction or communication with industrial partners. We learned that everybody thinks about my own solution, my solution in robotics, my data models, and of course, certainly my production and scale-up ideas. but we need at some point share or interact and share our data here, and this is one of the big obstacles. So coming back to what I've said initially, this very traditional industry of paints and coats has its mantra of, I'm the expert, I know what I do, but under the pressure of the Green Deal and seeing more and more often the benefits of digitalization, readily available data, and models built with these data, they kind of start embracing the opportunities of the. All right, that's the end of my presentation. I just want to thank you to our funding agencies and especially to our partners from the DNL HIT project who helped developing the iHit solution engine concept and gave us the chance to build some first success stories.
Thank you very much for your very nice presentation. And do you have any questions related with the presentation? I would like to see, I mean, this very innovative approach, machine learning, this is something that we would like to use at the synchrotron as well. So I see that it's a very promising technique or innovation. So this is very interesting. I hope that we can use it under synchrotron very soon. Okay?
Well, I'm pretty sure you can.
Okay. Thank you, Jost.
Thank you.
So,